Hi and welcome back. Today I'd like to perform a goodness of fit test. We are at the point in the term where we're familiar with the normal distribution, we're familiar with the t-distribution, and now we're going to get familiar with another distribution, which is the chi-square distribution. The goodness of fit test, the test statistic will be a chi-square test statistic. So a little bit about that. The characteristics of the chi-square distribution is that it's not symmetric. Its shape depends on the degrees of freedom, just like a student t-distribution. As the number of degrees of freedom increases, it becomes more nearly symmetric. And as the values of chi-square are non-negative, that is, the values of chi-square are greater than or equal to 0. So I have a little picture here. Page down. If you're trying to visualize this, you can picture the curve. Here in blue, you see when the degrees of freedom are 2, and I'm just going to kind of redraw that. When the degrees of freedom are 2, you have a extremely skewed distribution, right skewed. As the degrees of freedom become larger and larger and larger, and you see the last one, degrees of freedom are 30, we're approaching more of a symmetric normal curve. So that gets you a little bit familiar with the shape of the chi-square distribution. Much like the t-distribution, when the degrees of freedom become larger and larger and larger, it starts approaching that normal distribution. Okay, let's take a look at the first example problem. I'll read it with you. A sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their grandchildren is different today than it was in 2000. According to the U.S. Census Bureau, in 2000, 22.8% of grandparents had been responsible for grandchildren less than 1 year. 23.9% of grandparents have been responsible for their grandchildren 1 or 2 years. And 17.6% had been responsible 3 or 4 years, and 35.7% of grandparents were responsible for more than 5 or more years. If the sociologist randomly selects 1,000, I'm going to highlight that, 1,000 caregiving grandparents, compute the expected number within each category, assuming the distribution has not changed from 2000. Okay, so this notion of expected counts. You've got 1,000 trials of the experiment, and your sample size is 1,000. So the expected counts are 1,000. So expected count for less than 1 year is 228. The expected count for 1 to 2 years, notice how they're doing that. We're just taking the relative frequency times the sample size. So remember here were the relative frequencies. So 22.8%, 23.9% as a decimal is what you're seeing here. Okay, so the expected value then, expected count for 3 to 4 years is 1,000 times 0.176. And again, you're seeing where those decimals came from. So a lot of people say, all right, we'll just take n times p for the expected count. Okay, so once we get our expected counts, let's see what we do next. We get ready to run the test, and you'll notice in the chi-square test statistic itself, it's observed minus expected squared divided by expected, and then you sum that up. So to get the chi-square test statistic, you would take your observed values minus your expected values, counts, square them, divided by each respective expected count, and sum it up. Now, I don't require my students to do this by hand. We're going to get from computer, but I think it's nice to know where it came from. The chi-square, it will follow the chi-square distribution with k minus 1 degrees of freedom, where k is the number of categories that you're looking at. Okay, we'll take a closer look at this. The requirements to run the chi-square goodness of fit test is that all expected frequencies are greater than or equal to 1, and that no more than 20% of the expected frequencies are less than 5. Let's inspect our data now. I do have a little note here, a little reminder. The goodness of fit tests, let's take a look at this note here. The goodness of fit tests are used to test hypotheses regarding the distribution of a variable based on a single population. If you want to compare two or more populations, you're going to use tests for homogeneity, which are in the next section that we talk about in my next podcast. So let's run the goodness of fit test. Your null, it's important to know what your null and research hypothesis is going to look like. So it's going to be H naught is going to be the random variable follows a certain distribution, and H1 is going to be the random variable does not follow the distribution that is stated in the null hypothesis. So if we revisit that data from the 2000, the Census Bureau data of grandparents that care for their grandchildren, okay? So you see I've revisited that same problem, but now I ask this question at the end. If the sociologist randomly selects 1,000 caregiving grandparents and obtains the following data, so here we have the data from those 1,000. Here it is. So this is the data that he obtained from that 1,000 that he sampled. Now what I did was I took that data, the frequencies, you can think of that as a count. So big note to self. Frequency means the same thing as the observed count. And remember, for the chi-squared test statistic, you're going to take your observed count minus some expected count. And we had already got those expected values. So I put them in Excel already. Let's take a look. Okay, so here you see I have the observed counts, and then those expected counts that we had gotten when we took n times p, the relative frequencies, times the sample size of 1,000. So we did that in step 1. So when you're running this kind of a test, you always want your observed counts and your expected counts. That's your trigger there. Okay. Now let's go back to the question. So I've written this out here a little more formally. Test the claim that the distribution is different today than it was in 2000 at the 5% alpha level, or level of significance. We had already said what the null and research hypothesis is going to be in this kind of test in general, but I applied it to this problem. So the null is that the distribution for the number of years caregiving grandparents are responsible for their grandchildren is the same as it was in 2000. Or your research hypothesis, your H1, is going to be that the distribution for the number of years that the grandparents are responsible is different today than it was in 2000. Now remember, you never actually accept the null as being sheer truth. You can only fail to reject it. So we'll see what decision we end up with. We are lucky because Megastat and the TI-84s, not the TI-83s, but the TI-84s, have this built in. Let's take a look. So we go add-ins, this test built in Megastat, go down to chi-square, and you'll see that goodness of fit is an option. And it says, makes it pretty obvious, observed values, so we're going to highlight the observed values. And then it says expected values, so we're going to highlight the expected values. Counts. Leave this one blank right here, I'll just leave that blank, and hit OK. Now, what we're going to do, and I'm going to see if it'll let me, I'm going to zoom in on here. What we're going to do is retrieve the information that is most important to me for this course, since I'm not, I mean, this data here is interesting because it shows you that it's actually computing that chi-squared test statistic, which ends up being 6.605, so one could easily do that by hand as well. But yes, your chi-squared test statistic we would report as 6.6. Your p-value is you can see down here, is 0.0856. 0.0856. And now you're good with decision rules. You know since p is greater than alpha, you know we fail to reject H naught. And that means that we do not have enough evidence to support the alternate hypothesis that said that the distribution significantly differed from 2000. So we basically, in the end, we do not have enough evidence. to support H1. So the distribution does not differ significantly than what it did in 2000. Okay, hope that helps. That will be your goodness of fit test. And like I said, I won't require you to do that by hand this term.